All right, hi everybody. Welcome back to Wednesday, where I wasted my whole day kind of doing nothing, and now it's like 12:20, and I'm making 12:20, and I'm making a quick video. So yeah, quick little note before we begin. Today is Wednesday. Today's Wednesday for me too. Usually I'm like making the video the day before, and I'm like, whoa, what day is it? Now I know that it's Wednesday and the video is for Wednesday, so that's kind of fun. But quick little note about Wednesday. On Wednesday, I kind of have the schedule pulled up over here. On Wednesday, I am allowed to have office hours from 1:15 to 2 o'clock. So I kind of did this during the active God days, and then I just kind of stopped. I had some reasons for stopping, and that the schedule wasn't clear, and I didn't know like, oh, which class do I want to set up for which day, because I only get 3 days a week and I have 2 different classes. But now I'm kind of realizing that I don't really care, and I just want to talk to you all. So if you want to come to office hours to ask questions, go for it. But really, I just want to catch up because I haven't seen you all in a long time, and I miss you guys. So yeah, so 1:15 to 2, I'll kind of set up a link for Zoom. If you want to ask questions, go for it. But if you want to kind of spend this as a time to catch up, I would be very excited about doing that. But yeah. So yeah, that's what I got going on. But yeah, so what we're gonna do. Wow, how many times can I say? But yeah. So yeah, what we're doing today is we're looking into using Newton's universal law of gravitation to explain how tides work. So what we're going to do today is really quickly, we're going to look at this cool video of tides. I really like this video. And then I'll go through a quick review about gravitation, gravitational fields, all those good ideas. Then I have some practice questions, and then a free response question in the Google form. What's going to be due of you guys is the 3-question Google form that's kind of like quicker questions, more conceptual, and then the longer, more AP style free response that we're going to see on the AP test. And just like I did on Monday, I'm going to give this to you and be like, hey, here's 2 days for it, Wednesday and Thursday. Just because I like that a little bit better. It's less hectic for me. Hopefully it's less hectic for you, so you kind of have less stuff to do throughout the week, because I know I was giving a lot. I'm sorry about that. And yeah, kind of spacing it out at your own time, at your own pace. So this is going to be for Wednesday and Thursday. But so what we have to start out with is, I thought this was so funny. I Googled the word tide, and then it just popped up with the tide logo instead of like tides. And I was like, haha, peak of humor. So I just put that in there. Again, it's late and I scrambled for this. But so this is kind of a cool video. Oh, I didn't know the music was so funky. But so we have this progress of the day at the Bay of Fundy. And we see the boats go lower because the water is getting lower. And then, just you wait, this is crazy. This is actually wild. Like, it's not just like a normal tide. It's like a deep tide. Like, look at this. Now there's no water. Crazy. It like dries up. That would stink to own a boat here. Like, I can't imagine how the bottom of, well, these people just walk in like it's no big deal. I didn't notice that before. That's crazy. And then it goes back up. So yeah, owning a boat would be stressful. I feel like the bottom of your boat would be scratched up. Yeah, so probably if you want to go into boat insurance or nautical insurance, this town would be one to avoid, I'll tell you that much. I'm sure these things have got to like tip and stuff. Oh, I guess they're like very secured. Huh. Whack. So that's my commentary. Maybe I'll become a commentary YouTuber, or I'll just do commentary about this. Nah. But so yeah, what we want to talk about is what's going on here and how does this tide work? So it goes in, it goes out. That was a hot meme back like 7 years ago, where a person was just like, oh, well, how do tides work? Nobody can explain it. They go in, they go out, but how? So yeah, we're gonna be able to answer this question today of how do tides work. So to start this off, let's kind of think about gravity as a whole. So it's no secret, that's the word I'm looking for, secret, it's been a long day. It's no secret that we're going to be looking at gravity, because I kind of started us off being like, hey, gravity's a thing, let's remember that. So we're looking first, kind of zooming out and linking our prior learning, what we did with centripetal forces, to what we're doing with gravity and gravitational forces. So if we think about something like this satellite or this moon or whatever I drew, I kind of wanted to draw a satellite, but it looks more like a moon. If we think about an object that is orbiting the Earth, really that just means that this object is rotating around the Earth. And if we kind of zoom out at it and look at it more from this perspective as opposed to this perspective of the International Space Station, if we zoom out, we can see, oh, well, it's making this circular path, it's making this circular motion around an object. Excuse me, sorry. And we know about circular motion. We just learned all about it. So we said that in order to have a circular motion, or in this case what we're going to call an orbit, we need some sort of centripetal force. That was kind of our main idea in the last little video, the last little set of lessons. So what we need is a centripetal force to keep our object moving in a circular path. And in this case, we have a circular motion, which means that there's some sort of centripetal force that's keeping our object in a circular path. So the force that's doing that when we're at this long range, if we like circle our object, we'd be like, hey, like, oh, I spoiled it. I thought I had a thing we're circling it. I'd be like, hey, there's no contact forces here, so I must have some sort of long range force. And this long range force that's keeping our object in this centripetal motion, this circular motion, or our centripetal force, is the force of gravity. It's acting inwards to pull our object in and maintain this circular motion. So this is really interesting. This is a cool idea. So one thing we want to think about that's kind of going to springboard us into our future learning, our next little bit of learning about gravity, is like, well, how does this gravitational force work? Is there a gravitational force between the satellite and the Earth, even though the satellite is in space? And yeah, well, the answer is yeah. And kind of thinking like, hey, does Newton's third law still apply? This idea that we have these equal and opposite forces. So that feels weird saying, okay, well, we know that the Earth is applying a gravitational force to the satellite, but if Newton's third law is holding up, that means that the satellite is applying an equal and opposite force, a gravitational force on the Earth. That feels weird. Like that applies to us too. We are applying, or the Earth is applying a gravitational force to us. Are we applying a gravitational force to the Earth? That's really weird. And the answer is absolutely yes. It's one of Newton's laws. It's a law. It has to apply. But so within this Newton's law, there's a lot of ideas that come out of this. There's a lot of big ideas that are going to help us with our further learning of gravity. So there's this idea that yes, we have, if we're looking at this and calling it a satellite, there's a force of gravity on the satellite by the Earth, and then a force of gravity on the Earth by the satellite. So both of these objects, they have mass, and both of them are applying a gravitational force on each other. So that's kind of weird. There's a gravitational force acting on the Earth caused by the satellite? Oh, I was asking like a question like, what? There is. And what's causing this gravitational force is this idea that the satellite and the Earth and really every object in existence in the universe has mass. Well, all the objects that have mass have a gravitational force that's associated with them. So we kind of talked a little bit back, maybe like one lesson ago or two lessons ago. There's this idea of where we have this inertial mass, this F equals ma mass, and then we have this gravitational mass. And numerically, they're the same thing. They both are the same number. They're going to be experimentally the same exact idea. But gravitational mass is this kind of how much gravitational force do we have, whereas inertial mass is just like, hey, how much force would we need to move it? So it doesn't really matter the distinction. AP makes it, but whatever, it doesn't really matter. But so the satellite and the Earth, they have this force that's acting on each other. They both have gravitational forces acting on each other, and both of these objects have gravitational mass. And gravitational mass is the property of an object or a system that determines the strength of the gravitational interaction with other objects. So pretty much this idea that if you have more mass, you're going to have stronger gravitational force. You're going to have a stronger gravitational interaction. Gravitational force describes the interaction of one object with mass with another object with mass. We saw here the satellite has mass, the Earth has mass, and these two things, because of their mass, they interact with each other. There's a gravitational force between them, and the mass is dictating how much force there's going to be. So any two objects with mass have a gravitational force between them, and the mass is telling us, hey, how strong is this force going to be? So these are some ideas that we have going on, but let's put a little bit of math to that. Let's put some equation to this. So we have, yes, this interaction because these two things have this mass, and this interaction is really dictated by our equation for gravitational force. This idea that there's a force associated with the interaction of these two objects. So when we're looking at the gravitational force, a few main ideas jump out. And one of the main ones is that this gravitational force is always attractive. If we had kept on going with learning, we would have seen a very similar force. We would have seen an electric force where we can have attractive and repulsive particles. But with the gravitational force, it's always going to attract. It's always going to pull these objects closer together. Always going to, well, maybe not closer together, but it will pull these objects. It will attract. So gravitational force is always attractive. It'll never repel. That'd be crazy if you were like standing on Earth and then you just like were suddenly pushed away by the Earth. So the magnitude of the force between two spherically symmetric objects of mass m1 and m2 is just going to be g m1 m2 over r squared, where r is the center-to-center distance between the objects. So pretty much that sentence is summed up by this equation down here, telling us the gravitational force is equal to this gravitational constant, this capital G, times the mass of one of our objects, the mass of the other object, divided by the distance between them squared. And when we talk about the distance between them, we really say, hey, from the center of one of our objects to the center of our other object. So like us right now, we're standing on the surface of Earth. We're some distance away from its center. So that r, it's not 0, it's whatever the radius of the Earth is that I don't remember off the top of my head, but hey, that's okay, that just means I'm sane. But if we're looking at this situation, again, this is just a little simulation. I know we played with this when we first started this out. If we increase the mass of one of our objects, we see, oh, that gravitational force increases. If we increase the mass of our other object, oh, that gravitational force also increases. And if we change the distance between them, the closer we get, if that r goes down, then the gravitational force goes up. So we see all of these interactions happening in this simulation, which is kind of neat. And I can close out of it. But so yeah, as the mass goes up, gravitational force goes up, mass goes up, gravitational force goes up. As the distance goes down, that gravitational force goes up by a larger factor. All right, and then this is kind of, we touched on it a little bit when we were learning gravitational force, like I kind of mentioned it, but now we're gonna kind of be a little bit more specific about it just because we have the time, we have the ideas with it, and I feel like we can handle it, I feel like we can do it. It's kind of a tricky idea to think about, but hopefully that this will be okay. So we've been talking about the gravitational force. One other thing that we can look at to make our life a little bit easier, and we do this all the time, is looking at this number of the gravitational field, this concept of gravitational field. So when we look at a force, we talk about the interaction between two objects. We say, hey, you have to have one object and you have to have another object. An object can't exert a force on itself. But when we're talking about gravity, a lot of the time we want to talk about just one object. Like if I want to talk about Earth, I usually just want to talk about the gravity on Earth. I don't want to talk about the gravitational force between me and the Earth. I just want to say, oh, I want to say the Earth has a gravitational strength of 9.8 meters per second squared. Or if I'm talking about another planet, I don't want to just be like, hey, if you went to this planet, you would feel a force of this. I want to kind of talk about a general number. I want to talk about a general expression that will apply to the planet and not an individual's interaction with this planet. I don't want to talk about a force. I want to talk about a property of that planet. I want to talk about the property of the space around that planet. So what do we want to talk about just the gravitational strength of just one object? Well, we do it all the time, and we talk about the gravitational strength of Earth, which is a useful number. We know it is 9.8. It's useful to talk about. 9.8 meters per second squared, or newtons per kilogram. But so with the gravitational field strength, what it measures is how much gravitational force we would have if we placed a mass m at a certain location near an object with mass big M. So we'll talk about this in a little bit. We'll talk about what this means. I just want to kind of go through the formal definitions. A gravitational field G at the location of an object with mass little m causes a gravitational force of magnitude mg to be exerted on the object in the direction of the field. And the gravitational field is a property of the object that is creating it. And really all that it is, it's a quick way to think about the force. It's a quick way to talk about how strong a force would be. So really the main idea from this that we want to get out of it is a property of the object that is creating it. The Earth has mass, and that mass creates a gravitational field. And pretty much this sentence is just saying we can use the gravitational field strength to figure out the force by just multiplying m times the gravitational field strength. and it's pretty much saying if we were to place a mass in there, how much force would that mass feel? So that's a lot of words. I feel like it can more be easily expressed with numbers. So I kind of have, let's get back to that. So when we talk about gravitational field strength on Earth, we say that the Earth's gravity is 9.8 meters per second squared. So what we're really saying is that at a location at the surface of the Earth, the gravitational field strength is 9.8 meters per second squared. And we can use that number to then quickly calculate the gravitational force that an object of mass little m would feel at the location. So we're used to doing this. We're used to saying, hey, what's the gravitational force that an object of mass 2 kilograms would feel on the surface of the Earth? We'd say, oh, I know that the force of gravity equals m times this g, the gravitational field strength. So we're going to do 2 times 9.8. I'm going to say the force of gravity equals 19.6. And defining this quantity of 9.8 meters per second squared is really helpful because then we can look at any mass and figure out how much force it would feel. So if we look at this with 4 kilograms, we could say, okay, I'm going to put a mass of little m of 4 kilograms at the surface of the Earth. It would feel a gravitational field strength of 9.8 meters per second squared at this location, and I can figure out how much force I have. And that's really helpful. I've defined this quantity of the gravitational field strength, and then I know how much force an object of a certain mass would feel. And what we can do is kind of think about how the gravitational field strength changes as we change our distance away from it. So the further away we go from an object, our gravitational field strength will decrease. So we can define the gravitational field strength really at multiple locations. We can define the gravitational field strength at any distance away from a certain mass m, and once we've defined the gravitational field strength, this little g, we'd be able to calculate how much gravitational force we feel at that location away from our mass of big M. So if we're looking at this, maybe we're saying, okay, instead of looking at the surface of the Earth, let's look at how much force an object would feel at some further distance away from the center of the Earth. So maybe we look at it out here. Maybe the gravitational field strength is a number of 6 meters per second squared. Let's put our 2 kilogram mass there. We've defined the gravitational field strength at this location to be 6. So we can come in here and say, oh, well, if I want to figure out how much gravitational force I have there, I just have to do the mass of my object times the gravitational field strength at that location, and then I would figure out how much force I would feel. In this case, it would be 36 newtons. And then if I came in here and I said, well, instead of looking at this 2 kilogram mass, what if I look at the 4 kilogram mass? I'd say, okay, well, to do that, that's not too bad. Oh, 2 times 6 is totally 12. I don't know why I did that. Okay. So 2 times 6 is 12, so it would be a force of 12 newtons, my bad, sorry. So if I had a mass of 4 kilograms, I would put that at this location. The gravitational field strength at that location is 6 meters per second squared. So I'd say, oh, 4 kilograms times 6 meters per second squared, it would feel a force of 6 times 4, 24 newtons. So defining this gravitational field strength, it's a property of the mass, and what it allows us to do is quickly determine the gravitational force for any mass that we put into that field. So pretty much our main difference is the force. Gravitational force is this interaction between two objects. The gravitational field strength is this number that is just defined for an object of mass big M, for any mass. So every mass has a gravitational field strength around it, and we can define that at different distances. And then we can use that number to just quickly calculate the gravitational force that these objects are feeling. So if we want to actually find a number for the gravitational field strength, we did this a bunch. This was kind of like one of the things that you guys all hated when we were doing the universal law of gravitation, is kind of manipulating these equations. And I think it's tricky because the way that the College Board gives us the formulas is a little bit weird, because we go from M1 and M2 to just like a singular M right there. So what we're going to do really quickly is kind of define, let's say, what is the strength of the gravitational field created by this mass big M at a location r away. So we put this little mass little m there, but if we want to know about the gravitational field strength, we don't need that little mass m. We don't need an interaction between two objects. We just need one object and say, hey, what's the gravitational field strength around this big object of mass big M? So if we wanted to do that, we could kind of start off and say, hey, this little g is our equation for finding gravitational field strength. That tells us how strong is that field for an object. So we can say the gravitational field strength is equal to the force of gravity divided by the mass of some little object that we would put in that field, some sort of like test mass. And we can also say, well, the force of gravity is equal to this universal law of gravitation equation that we talked about earlier. This universal constant times the mass of one of our objects, mass of the other object, divided by the distance between them squared. So we can say, well, let's move this around a little bit. We can set this equation equal to force of gravity. This equation is already equal to force of gravity. So we can set them equal to each other. We can say mg equals gmm over r squared. And we say, hey, this little mass, it doesn't matter. The gravitational field is just a property of an object. We want to know the gravitational field strength the gravitational field created by this big mass m. So we don't care about this little mass. We care about just what's going on around the big mass m, big M. So we can cancel out this little m and say, hey, this little g is equal to big G times m, the mass that we're looking at, the mass that's creating the gravitational field, divided by r squared. So we can end up with this equation that says our little g is equal to big G times the mass that's creating the gravitational field over the distance between the center of our object and where we are looking at squared. So that's kind of how we can find this gravitational field strength. We can see again that it has this relationship to big M and r squared. So if the mass of our object is bigger, it'll create a larger gravitational field around it. And so bigger in terms of mass if it's more massive. And then if we go closer to the center of this object's mass, then our gravitational field strength will increase. So like if you climb a mountain on Earth, you're increasing the distance from the center, so you'd feel a lower G. So now we kind of have our tools to help us explain what's going on with the tides. So this is kind of my explanation for it. It's a little bit sketchy, but it's okay, it's fine. But so what we can do is, let's say that this here is the moon. So we're looking at the moon and we're saying, well, the moon is an object that has mass, so a gravitational field is created by the moon. It's creating this gravitational field around it. And we just talked about if you're closer to the moon, it has a stronger gravitational field. If you're further away from the moon, it creates a less strong, a weaker gravitational field. So the moon is chilling, it's going around the Earth. Right? We got the moon, we got the Earth, moon. And we're going to look at just the gravitational field that's created by the moon. So at different points throughout the day and the month, and I forget how astronomy works, but the moon will be at different locations, I guess throughout the day because tides happen throughout the day. The moon will be moving around the Earth. So the moon's gravitational field is kind of moving around the Earth. So there's going to be some times when the moon is at one side of the Earth, times where it's at the other side of the Earth. But let's kind of focus at this time that we're looking down here, where the moon is to the right of the Earth. Excuse me, sorry. So what we talked about was this idea and this equation that as the distance between our objects decreases, the gravitational field strength will increase. So as the moon kind of gets closer to the Earth, we can think about the Earth as having really these two sides. One side of the Earth is in a region of stronger gravitational field, and the other side of the Earth is in a region of a weaker gravitational field. So one side is feeling a stronger pull than the other. So we kind of have, let's see if I have, this is like the only stretchy object I have, this headband. It's not even that stretchy. So one side is feeling a lot of force. Let's see, is this gonna work out? Yeah, one side is feeling a lot of force and one side is feeling a weak force. So we kind of have this stretching. We have this greater pull on one side than the other side. So the Earth is kind of stretching and bulging and squishing so that it's kind of squeezing out to be more ovalish, more like eggy, I guess. So one side is feeling more force because it's in this region of stronger gravitational field, which means that there's a more greater force, which means there's a greater pull, which is kind of stretching our Earth, which is causing the water to bunch up, which is causing this region of high tide. And then if the moon were up here, the Earth, instead of squishing this way, would then squish this way, and we'd have this region of low tide. So that's kind of a rough explanation, but hopefully it's okay. Here's kind of a better picture of it, saying, hey, we have a stronger force, Over here we have a weaker force, so we're feeling a greater pull and we're kind of getting this stretching. All right, and then the last little thing I just want to kind of review about is this idea of like, hey, if you have this circular motion of an object that's in orbit, how could you figure out the orbital period, how long it takes to orbit? So we would start off and kind of link our prior learning and this new learning to this idea that, hey, gravitational force is based on this big G times the mass of one of our objects, mass of the other object, divided by the distance between them squared. And when we're dealing with forces, we have F equals ma. And we talked about when we have centripetal forces and circular motion, the acceleration is equal to the speed of our object squared divided by r. So that was a lot, but we can then kind of manipulate our equations and say, hey, if we want to figure out this velocity or this time period, or really anything, if we want to start off with this, what we can say is, well, our gravitational force is our net centripetal force. The only force that's pulling us inwards towards the middle of our circle is this gravitational force, and it can then equal our ma, mv squared over r. And then we can say, well, we have an equation for gravitational force, let's plug that in. So we can say gmm over r squared is equal to mv squared over r. And then we can say, well, I have the mass of my little object as part of my mv squared over r part of the equation. I have the mass of the little object as part of my gravitational force equation. So we can cancel those out. We can also cancel out one of the r's. Then we're left with gm over r is equal to v squared. We can solve this for v. And then if we wanted to figure out the time period, the time it would take for one rotation, for one cycle, we could say, well, I'm going around this circular path, so my distance is the circumference of 2 pi r, and then this t is the period, so the time for one cycle. Velocity is just distance over time, so we can say 2 pi r divided by the period, and then kind of sub in for velocity, and then solve, and we can solve for this period. But yeah, that's just kind of a brief little overview of everything. Maybe not brief, it feels like this is really long, I'm sorry. But so a little overview about gravitational force and gravitational field and finding the orbital period of objects. Then I'm gonna kind of have these practice questions for you to look at. But if you wanted to kind of stop here and just take this would be Wednesday and then do the practice questions for Thursday, totally fine, totally understandable. Again, this is kind of split into 2 days. But yeah, so hopefully that makes sense, and then hopefully I'll see you at the office hours.